I really appreciate the opportunity to be here today. Can everybody hear me okay? I see a few familiar faces out there. When we were asked to make this presentation, the question was, how do you guys handle the non-gaseous substances? Everyone knows how to handle the chlorine and the ammonia. We see that everywhere we go. But what about these non-gaseous materials? What do we do with those? And I had to think about it for a moment, because it's one of those things from my perspective, we've been dealing with it for so long, it becomes almost second nature. It's like somebody asking you, how did you put your shoes on this morning? Right? And you don't really think about it. You just do it, right? Put them on, tie it. But when you have to break it down and say, okay, what's really important? What we came up with is, for you guys, what's important is understanding those mechanisms when it comes to the solids and the non-gaseous materials. What results in the releases? What causes the releases? Understanding the characteristics, the behaviors of these materials. And so that's what we're going to try to focus on today. And with that, hopefully give you a better understanding that will help you, help industry, come up with mechanisms, procedures, policies that will really help eliminate or prevent potential releases into the atmosphere. At the end of the day, I think the goal when we look at most regulations is really to minimize negative impacts to human health and the environment. And there's a lot of ways we can do that, but the more information we have and the better understanding we have how these materials are released into the environment, the better capable we are in helping people to avoid such releases. So again, by understanding the factors or the mechanisms that result in emissions of solids and liquids, we can better assist industry in developing strategies to limit emissions under routine and emergency scenarios. This will in turn, again, help protect the public from uncontrolled releases of hazardous materials. We need to understand the materials. So that's really our objective in the first part of this. We're going to talk about the basic characteristics. And a lot of this may seem very rudimentary and things that you guys really know already. But I think it's important to, again, to take that step back and use that perspective when looking at these materials, because, again, it's going to give you the opportunity to better address those concerns. So non-gaseous substances, what we're really looking here is we're looking at liquids. These are materials that are liquid at ambient temperatures. They're not pressurized, right? Vapor pressure equal or greater than 10 millimeters of mercury. That seems to be a big issue when we talk about CalArp, especially when we're looking at things like nitric acid, right? In those situations where we're dealing with nitric acid with vapor pressures less than 10 millimeters, those aren't covered by the program. And then with our solids, again, this could be in a solution or a molten form or powders. And I'm curious, we've got some bodies here representing obviously different jurisdictions. How many of you now are dealing with facilities that have materials that are listed under CalArp that are either solids or liquids? What types of materials are you handling? Cyanides, the sodium cyanides, things like that? Okay. All right. Okay. All right. So how do those materials get into the environment? So you gave us some examples of things that you're dealing with. I think one that's going to become even more important over time with the change to electric, energy for our cars and hybrids and so forth, lithium hydride used in a lot of the batteries, right? We're going to see a lot more of that in facilities dealing with batteries, whether it be recycling facilities or just processing facilities. But some examples, cadmium oxide, we talked about the sodium cyanide. So those are some common examples. Same thing when it comes to liquids. The nitric acids, the hydrochloric acid, aqueous ammonia, formaldehyde, the peracetic acid, and the acrylonitrile. But what do you see in this picture right here? That's not a liquid, right? Really what we're dealing with is a particulate, a fume, a vapor coming off there from the reaction of the nitric acid. One of the things that we want to think about is when we look at these liquids and solids is how do they react with other materials? Because now I'm not talking about a release of nitric acid, right? It's reacted with something, so it's a whole other type of release. We're not going to focus on the gaseous releases. You guys have already dealt with that before. Today we're going to talk about what mechanisms result in the introduction of the solids themselves or the liquids into the environment. I think, again, the gaseous portion of that, or those things that result from the reaction, people are pretty familiar with. So when you go into a facility and you look at the sodium cyanide, that's being stored or processed, what are the mechanisms? What are the typical things that you worry about? How is that material going to be released into the environment? From a simple storage perspective, not a lot that's going to cause it to be ejected. I mean, what have you seen? What have you seen when you come into a facility when dealing with the sodium cyanide?
Typically a planing mat.
Right. And so they have a storage area with the solid in a container, in a secondary containment system, and then they'll put that into solution. And then once it goes into solution, now you've got another issue that you're dealing with. So now it comes from a solid to a liquid. But what's going to cause that solid, as it's in storage, to be emitted in the atmosphere? It's really either it's going to be blown, right? If there's maybe somebody's handling that sodium cyanide when they're bringing it into the facility, maybe a package ruptures, right? Then it goes onto the ground and it gets entrained into the wind. And then actual ejection, if it gets picked up into some sort of pneumatic conveyance system, if it's being conveyed pneumatically to be loaded into a process. It could be a solid that's used in some sort of ventilation system or in a controlled system, and it gets picked up into the ventilation. Is that storage area close to an air return? But for solids, other than that, they really just sit there. Right? There's not a lot to drive them into the environment. Liquids, same type of thing, except we add one: volatilization, evaporation. Right? What happens? And then the question is, what are the characteristics of these materials then that impact these typical release mechanisms? Solids, right? The size of the particle. How big is the particle? Lighter particles are more easily entrained in the wind, right? More easily dispersed. If I have a large particle size, it's more likely to, if it is picked up in the wind, to drop out because of gravity. Right? So these are the things that we look at when we look at solids. What are those mechanisms? Okay. So we look at the characteristic of the material, and we will also look at, again, how is it being stored? Its proximity to those systems or those processes that could result in it being entrained in the wind or ejected into the atmosphere through some sort of ventilation system or pneumatic conveyance. So again, when you go into a facility, those are things that you're going to want to be looking for, or if you're reviewing an RMP. When we talk about our liquids, again, we look at those same types of things, but now we worry about temperature. What is the process temperature? And then what are the flash points and boiling points associated with those liquids? Because that's what's going to drive the evaporation of that material, right? How is it emitted into the atmosphere? So what are some basic characteristics of solids? We talked about it. In storage, they're easily contained. Right? There really is only a limited potential for a release to the atmosphere. We worry about the particle size distribution. Right? How big is that particle? If I had a pile of rocks here versus some talc powder, everybody's seen LeBron James, and he throws it up in the beginning of the games. You see it disperse everywhere, right? You don't see that. Again, it's the particle size that affects the dispersion. Most of our facilities that we deal with, we're not going to see big dust clouds coming from them like this. Not because the particle size that they're dealing with isn't that small, but just because the volume of the solid material that they're handling isn't that large. But what that picture illustrates right there is how easily small and fine particles can be entrained into the atmosphere and then spread across an area. The other thing that we have to worry about are possible reactions. How is that solid material stored? Yes, it's easily contained, but if it's improperly stored and has the potential to react with another material to result in an emission of another substance, then it becomes a concern. And too often, I think when we talk about evaluating alternative release scenarios and worst case release scenarios, we ignore, or it can be ignored, the possible reactions of those materials. And so we look at the solids and we say it's really simple. Sodium cyanide is not going anywhere. But if I have a facility that's storing it, and I've got acids in that same area, now I've got the potential for the generation or the production of hydrogen cyanide gas, and now I'm dealing with the release of a gaseous substance. All right? So at the end of the presentation, we're going to talk about some of those mechanisms that you guys should be looking for when you go out into the facilities that will help the industry minimize those types of things from occurring. Oops, sorry. Solid in solution, that sodium cyanide now becomes part of a plating bath, right? We're going to deal with it now. So even then, the release of the sodium cyanide itself, because it's now in solution, the release of that material to the atmosphere is not likely. All right? But again, you've got to evaluate the potential reactions that will occur when that material is in solution. How will that be impacted? What engineering controls may be in place at that facility already? What happens if those engineering controls fail? Right? Those all impact the quantity and the nature of that release. Characteristics of liquids. They can be contained. Solids were easily contained. Liquids can be contained, not necessarily easily. They do have a higher likelihood of volatilizing, right? Depending on the surface area that they're being spread against, the temperatures, and the individual characteristics of that liquid material. What is its vapor pressure? What is its boiling point? Right. Again, the possibility for reactions. It's more readily available to react with other materials because it's going to spread more quickly. And again, all this is basic information, things that you guys probably already understand. But again, what happens is, just like putting on our shoes in the morning, a lot of it we just take for granted. And when you're really evaluating an RMP in a facility, you need to back up almost to the basics and say, okay, what's going on here? And then again, how is that liquid affected by operating conditions, temperatures, processes, etc. So now we understand, or at least have an idea of some of the basic characteristics, some of the basic things that can affect emissions of these materials. But the question is now, how do we calculate the release rate? All right. What do we use to determine how this material is going to be emitted? If you're looking at trying to figure out a toxic endpoint, where does it take you? How do you get there? And again, with liquids, we look at the area covered by the spill, right? And if everybody knows the regulation, we're looking at, it's going to disperse basically to a 1 centimeter thick spill throughout the facility. So that talks about surface area. Why is that important? Because the more surface area you have, the more potential for volatilization you have. The air to surface interface, the air to liquid interface is greater, so you have more evaporation. So you actually have a potential for a larger air release when this material spreads to a 1 centimeter thickness throughout the entire facility or over the area in which it's been spilled. Surface characteristics. What is the type of the surface that it's been spilled upon? That dictates, again, how fast that material will move and how easily it will be, or what is the likelihood of you being able to contain that in a smaller area so that, again, you can reduce that surface or that air to liquid interface, that relationship between those. The smaller you can make it, okay, the less volume of emissions you're going to have. Temperature is going to be important because, again, as temperature increases, we increase the potential for the evaporation of that material or the volatilization of that material. And again, those two there are related, the volatilization rate. Solids, where has it been released? Okay. Is it inside the building or outside the building? If I have a spill of sodium cyanide inside my production building, what is the likelihood of that release impacting off-site receptors? Pretty small. Okay? It's going to be a minimal potential because it's those mechanisms that we worry about. Remember when we talked about what are those mechanisms that can result in a release? Wind entrainment and ejection through some sort of pneumatic conveyance are much less when I'm inside the building. I've got a controlled area. But if I'm outside, I'm handling that material during storage, during unloading, or maybe process solution makeup, there's a greater potential, because now if I drop that material, it spills out onto the asphalt in the parking area or in the loading area, and I don't clean that up or respond to that effectively and quickly and efficiently, then there's a high potential that material is going to be entrained into the wind, right, and travel offside. When it comes to a solid, one of the things that's sort of odd when we start talking about release scenarios and calculating toxic endpoints is the regulation says that you have to look at that release rate as it occurs over a 60-minute period. The reality, in most cases, when you're dealing with a plating facility or even small, people handling small quantities of fertilizers and things like that, that spill handles in a very small area under a very short duration of time. And so when calculating the release rates, you have to look at it over that 60-minute period, and that typically will actually result in a reduction in the overall toxic endpoint when you spread that over a longer period of time. So one of the things that we look at to be more conservative is we look at that spill or that release when we do these programs occurring over a very small unit of time, because that increases your concentration. All right? Because again, we're trying to find out that worst case, a more realistic release type scenario. And then again, what is the state of that solid when it's been spilled? Is it in a powder? What is the particle size distribution? Again, those things all affect the release rate and how you estimate those emissions. So we've talked about that a little bit, but now we need to figure out how to calculate the actual emissions. And how is industry, when they submit their RMPs to you, how are they calculating those emissions? What is the basis for those emissions? And I think what's important is I'm a certified permitting professional with the South Coast Air Quality Management District, as was noted earlier. And one of the things that I've learned in my 20 years is that there's no one situation identical to another. And so what happens is we have to use proxies for estimating emissions. Essentially, one of the things that we're going to do is that we're going to start off with engineering factors. And these are factors that have been developed over time through source testing, through different studies. But again, they're conservative methods used to estimate emissions of different substances from different processes. We can use those same techniques in estimating the release rates of solids in order to determine what the emissions are of a substance in the event of a spill, okay, or a release. So some of the basic, or some of the available sites, the EPA's emission factor sites under AP42, WebFire, and we put the URL there so you can have access to that. The Emissions Inventory Improvement Program, and then also most of your local air pollution control districts will also offer some sort of database or grouping of emission factors that they use typically. But even then, how are you going to estimate how much is emitted when I have a 100-pound bag of sodium cyanide and I'm walking into a facility and I'm carrying it in to put it in a storage area and the bottom drops out and it spills onto the concrete? How do I estimate the release from that? I cannot find, and I challenge anyone here to look on these emission factor sites to find emission factor for that particle size or for that particulate matter in the event of a spill from an open bag or a broken bag. It doesn't exist, I guarantee it. So now what do you do? How do we determine what that emission rate is? This is where we have to look at those similar processes, find out the similarities between the process, the nature of the material, right, and the mechanisms that could cause it to be emitted. So for example, there under AP42, there are emission factors for rock crushing. There are emission factors for paint mixing, handling dry powder materials. There are emission factors for ink handling, conveying cement. So now we go through that. So if I had that bag of sodium cyanide, let me ask you guys, if I just gave you 3 samples, aggregate crushing, paint mixing, or cement pneumatic conveying, what would you choose as being the most representative emission factor? The cement, right? Because of the particle size distribution, right? Now, there's a little bit of a trick in that, though, because under the cement conveying or the cement emission factors, you're talking about putting energy into that system because it's pneumatic conveying, right? Now I've got a bag of sodium cyanide that I just dropped. The only energy going into that is gravity, right, when it drops. So in this case, I would actually probably select the paint mixing emission factor, where somebody's actually taking a solid and dumping it into a mixing vat. Okay? So again, the emission factors are there. The work, and it's somewhat subjective, is finding the right emission factor for the process that you're dealing with. And again, I can't sit here and tell you today every emission factor for every process that you might come into. What I want to do, though, is I want to leave you with some basic concepts that you can use when you're evaluating RMPs, when you're looking at how people are estimating these releases. Are they using emission factors that are legitimate and appropriate for the process that you're dealing with? Right? And it's going to take some time. And it's not, like I said, every situation is unique. Every time you come into a situation, you have to understand, again, what are the mechanisms? What are the characteristics of this material? What are the processes that are resulting in the potential emissions? And then by doing that, you can actually identify emission factors that are going to be relatively representative for that process. So now we've calculated some emission rates. And from here, it really, once we've got the emission rates established, the process is very simple, or very, I should say, similar to how we would deal with our gaseous materials. And we talked about modeling. And I actually brought an associate with me, Peter Stein, who is available if there's questions about modeling after the class. But we can go into it. But I just want to cover, again, some of the commonly used models. Once we have the emission rate of these materials, then how do we determine what the impact or what the fate of these materials are in the environment and to the outlying community, right? The off-site receptors. Where do they go? And how do we determine that? And there are three really commonly used models that we're all probably familiar with already. The RMP comp, Screen 3, and the ISCST3 air mod. Okay. How many of you here have actually ever done any modeling before? Okay. How many of you like it? A few. And here's the problem. Inherent to every model, there are limitations. So how accurate is that information, right? And how are we going to be able to make sure that that model truly represents what we're trying to accomplish? So those are always things that are in the back of our mind when we're doing these projects. So I think from anybody's perspective, when you're doing modeling, you're always going to be aware of that. One of the things that we try to do is we look at the limitations associated with those models to try to make sure that we've got at least the most conservative model to show, again, what would truly be a worst case scenario. I'd rather over-engineer something and make sure people are safe than under-engineer. So let's talk about the advantages and disadvantages. For RMP comp, first of all, we don't necessarily have to know specifics about any certain chemical. Those chemicals are already entered in to that model. The characteristics of those chemicals, how they're going to behave in the environment, all that data is already there. So it automatically calculates an endpoint based on input parameters. Okay? List of chemicals includes 77 acutely toxic substances and 63 flammable gases and volatile liquids that are in the federal regulations. The problem is it doesn't account for our solvents. Right? Those are not included in RMP comp. So would it be an appropriate model in these cases? Probably not. Again, there are some also disadvantages and limitations based on the distance to the endpoint is measured to the nearest 1/10 of a mile. Okay? All distances shorter than 1/10 of a mile must be reported as 1/10 of a mile. So there's some limitations in the accuracy and the degree of accuracy associated with that model also. And again, it does not include our substances, sodium cyanide, cadmium oxide, okay, those solid materials. So probably not an appropriate model when we're dealing with, again, the solids. But again, we do look at properties of the liquid, the type of scenario, the quantity released, the type of surrounding, and what mitigation measures are impacted. For toxic substances in solution like ammonia, formaldehyde, hydrogen, chloride, you need to know the concentration of the substance in the solution and the temperature of the liquid. Pretty basic information that you're going to be able to get. In most cases, you have that already in a business emergency plan or chemical disclosure that's submitted for facilities. You select the type of scenario. Either it's a worst case or an alternative scenario. And depending on the type of scenario selected, it will provide you with an output. Okay? Your inputs for the type of surrounding, urban or rural, very simple selections. It's a very simple model to use, and that's why a lot of people like it. A lot of the work's already done. The problem is it has limitations, so it doesn't become our model of choice. Screen 3 is really a summary of the ISCST 3 air mod. It's not truly the full model, but it does have some advantages. You're able to model the CalARP substances that aren't on the federal list, that aren't in the RMP comp, right? So you can actually model some additional materials. But again, it is a screen level model. It doesn't require the use of any chemical specific information. And it's a minimal amount of inputs that still gives you some pretty good data, okay? There are some limitations still. It is a DOS-based program. You've got to prepare your calculations of the emission rates outside of the model. And it's an iterative process for endpoint calculation, meaning that if you don't hit your endpoint, you've got to go back and recalculate and then do it again and run the model again. It won't give you the options. So you have to do multiple runs, which can become tedious and time consuming. But again, to pinpoint that exact toxic endpoint. The inputs on screen 3, very simple. Emission rate, type of source, is it a point source or an area source? Coming from a stack, or is it more of just over an area? What are the surroundings? Is it urban or rural? And then again, the distance to the receptors. Very basic inputs, very basic model, but it does allow you to model those materials, those parameters that you would not be able to model, or those chemicals, using RMP comp. So it's a step up. ISCST3 air mod. It's probably the model that we use most often. Again, you're able to model those CalARP substances that aren't on the federal list. It allows you to provide more specific data regarding the source itself and its surrounding area, the terrain, how is it configured. Okay? Specific information regarding stack height, building height, it takes into account downwash effects. How does the surrounding area impact those materials and the flow of those materials in the atmosphere? You can actually put very specific information about the particle characteristics when it comes to solids, when it comes to particle size. Because again, that's going to affect buoyancy and how it's entrained and how far it will move in the air, how gravity will affect it, how it will drop out. And it does allow for a very simple graphical interface. Again, some of the disadvantages, just like with the screen 3, the calculations are required outside of the model. It is an iterative process still in order to get to that endpoint. If you don't hit that right endpoint right away, you're going to be going through it multiple times. And it doesn't have a customized meteorological file. Yep, I'm sorry. So again, going through the inputs, it's a little bit more. We look at emission rate, source parameters, terrain data, meteorological data, and receptor distances. So you see that there's many more inputs in this model, but what that's going to yield for you is a more representative model of how these materials are going to behave. Yes. Yeah, so you can actually customize that file. And I believe you can also use actual metadata right from meteorological reporting stations.
Yeah, but if you need to do a specific stability class, you can press that file and repeat that data.
Right. So you can actually change that class within this program.
Does you need a standard
No, EPA doesn't. Because again, if you look at the federal list, you're not going to find solids on that list. So that's some of the limitations that you're dealing with. And so when you go through this, how do you represent, how do you find that model and those emission factors and those emission rates? So those are the limitations. So that's why we find this to be the most appropriate model in most cases. Okay. So within that, now we have an idea, finding those endpoints, how to calculate that, how to go through that. And I didn't get into the worst case scenarios. We didn't talk about alternative scenarios. But what I want to talk about now is really getting into, yes? The question was, is this the model where you have to use it to actually, or for a while to understand it and to get good at it? No, not necessarily. Again, understanding the inputs and where they go, it's straightforward. You can do it. I don't think there's anything tricky about it when it comes to that. It's just a matter of sitting down and going through the process. Because it's an iterative process, though, you may, over time, glean some better understandings of how to get to your endpoint quicker, what things you need to modify to determine what that is. But no, it's not difficult to use. Okay. And it gives you, again, more opportunity for flexibility. Any other questions? Again, we're going to open up for questions and answers in about 20 minutes, too, because I know there's going to be a lot of specific questions when it comes to the models and so forth, so we'll be able to field those. So feel free to, as we go through this, if you're thinking of anything, jot it down or just interrupt me now. It's fine. But, essentially, part of this is understanding what's going on in the factories or in the plants, also in the manufacturing sites. And what are they doing and what can they do to minimize the potential for releases when they're dealing with these non-gaseous materials. And as inspectors and you go out into the field, that becomes very important because you're going to be able to note a problem and an increased risk right away. And I'm sure most of you are very well trained in this already, but we're going to spend some time on that right now because I think it's important information for you guys, and I think it's also important to convey that back to industry because unfortunately, industry over time becomes complacent and they take things for granted. And it's really your job, our job, to help reinforce these things with them so that it becomes part of their culture, it becomes part of their everyday operation. And that's the biggest struggle I think that you guys have because no matter what happens, when you come into a facility, you're the bad guy, right? You're there to cause trouble. And they don't really see you there as, hey, you're trying to help, you're trying to minimize the potential negative impacts to human health and the environment that can result from their operation. But what we want to do is hopefully pass on some information to them and tools that will help them to control these non-gaseous materials better. So again, it's controlling the materials in the workplace. And the goal is to, minimizing potential releases during storage and handling, and then also minimizing potential release during routine use and processing. And they're very similar, but the tools that are available vary slightly. We're going to talk about storage first. And I keep going back to that storage of the sodium cyanide because that's always a very common one that we encounter with our clients. We do work for a lot of plating facilities. And some of the things that we try to stress with people, there's three basic categories where these controls fit into. Management practices, equipment and tools, and training. Right? And you guys, I know, are aware of those things too. But those really are the three categories that really come into play when we try to minimize negative impacts to human health and the environment as a result of release. We minimize those negative impacts by actually reducing the potential for those emissions. Right? How are they going to occur? So let's talk about management practices. Pretty straightforward. Segregation, container management, housekeeping, and the thing that ties it all together is inspection. Right? Pulls it all together. So segregation. We have solid materials. We know there's a potential for them to react. That's one of the mechanisms, or that's one of the ways that material can result in a release. So we segregate it from those materials that it could react with. Straightforward. I know you guys know that. But a lot of our industry, unfortunately, gets complacent and they don't. Housekeeping. Humongous. humongous. 90% of the battle is housekeeping. Keeping materials stored in the proper container, keeping materials stored in the appropriate storage location, making sure that spills are cleaned up quickly. They don't remain on the floor for periods of time, because again, if I have a spill and it stays in an area for an extended period of time, I have more chance for evaporation, more chance for volatilization, more chance for wind entrainment, all right, or tracking. So we've got to get them to really maintain the housekeeping. Also, the housekeeping affects our secondary containment. If we have segregation and we have secondary containment and we have material that's spilled or in that secondary containment, taking up the capacity of that secondary containment, when we do have an emergency situation or a non-routine scenario, the ability of that secondary containment to perform as it's intended to perform is going to be compromised. And then again, container management. Using the right containers, making sure the containers are in good conditions, they're not leaking. I've got my bag of cadmium oxide or my box, and I'm carrying it over to the open process tank, and as I'm carrying it over, it's got a hole in it and it's dripping out behind me, right? Just pouring out over the floor or in the parking lot, but no big deal because I've got what I need in my box. Okay, making sure those containers are properly managed. The key to all this, though, that holds this all together is the inspection. If the facilities aren't doing inspections, and if inspections aren't an integral component of their RMPs, there's something missing. Okay, but they have to do the inspections because that's what's going to allow them to make sure that materials are properly segregated, that materials are in proper containers, and that the facility is implementing proper housekeeping procedures. It really is critical. So that's one thing that you'll be looking for when you look at the RMPs and you look at the implementation of those RMPs in the facilities. Okay? How are they being inspected? Are they being inspected routinely? Is somebody just pencil whipping? And you can tell when you go into a facility, right, if somebody's really doing the inspections or not, because it's going to be very, very apparent when you walk in. What equipment and tools are available to us when it comes to, again, trying to manage these materials in a storage type situation, solids and liquids, to prevent their releases into the environment? Labeling, of course, right? Making sure that materials are properly labeled and that MSDSs are available. Why is that important? If a material is not labeled, then how do I know what it is and how to store it properly? Right? Going back to our management practices. NFPA placards are important for employees to understand what hazards may be in an area when they're working in that area, and also for emergency responders. Secondary containment, again, a big component of that. Emergency response equipment, though, is critical. And again, that comes to spill cleanup. In most cases, what's going to cause a release, when we talk about a worst case scenario for solids and liquids, it's a spill. Right? When we're trying to evaluate what those endpoints are, what they result from, it's a spill. Those are the typical releases. And if we can't, or if the equipment isn't available to the facility to respond quickly and effectively to that spill, there's a higher likelihood for that material to be entrained, more of it to be entrained into the atmosphere, and resulting in air emissions and a greater impact to the outlying community. So again, when you come into a facility, is that emergency equipment there? Is it available? Is it functional? Right? Because again, remember, these materials, solids, are easily contained. Liquids are likely contained. Right? So again, these become important tools when we start talking about how those release scenarios may impact the environment and how we develop those. And then, of course, training is a critical component, and again, should be a component of the RMPs. Not only is this training required by other regulations, but it's an important component of any RMP because, again, it's that educational process, it's that information, that awareness that employers are giving to their employees that are working with these materials that are going to help minimize negative impacts to human health and the environment. We're going to increase their awareness, we're going to increase their understanding, and we're going to develop a culture within the workplace that's going to help these people work safely with these materials, respect them for what they are, and when they do have a spill, respond to it quickly, right? And don't leave it laying around, let somebody else come deal with it. They're going to understand it better. Very basic tools. So routine use, we talk about storage. Now we go to routine use. Now we're handling that material. It's in a process. And we're going to look at the same types of things. And they're very similar in nature when we look at these. The same management practices apply. The same equipment and tools. There's a few others, engineering controls and things that we're going to talk about that come into play. But also the training is there also. So again, similar things. So again, we've talked about segregation already. Same things apply. You know, making sure that incompatible materials are properly separated either by distance or by a barrier. You know, what happens if, you know, people are using materials in an area that are reactive with another material and they're not aware of those potential hazards, right? There's a potential for mixing there. Again, the housekeeping. Right? Making sure that process areas are clean, the equipment is well maintained. Making sure that containers are in good condition. Open process tanks aren't leaking. There aren't residues on the outside of the tanks. But again, it all goes back to that key point, inspections. That's how they really tie that all together. The RMPs should include those components, again, that detail what inspections are being conducted, what frequency those inspections are being conducted, and what criteria are to be inspected for. And when you go out to the facility and you're verifying the implementation of the RMP, you're looking to make sure that those criteria are appropriate and applicable to the process, again, based on the mechanisms and the behaviors of those materials that they're handling. When it comes to the routine use, the tools that we look at and the processes are repeated for the most part, but we also look at personal protective equipment and engineering controls. And the engineering controls are important when it comes to evaluating releases, release scenarios, because what happens when we start talking about alternative release scenarios is when we're handling this material, and we may have scrubbers, we may have air pollution control devices in place to limit the emissions, right, and the potential for those releases. But if that equipment isn't functioning, or if it malfunctions, or if it shuts down, now we've changed our whole release scenario. Right? Under normal routine operations, if that scrubber is functioning, it's designed to control or reduce atmospheric emissions of that material, whether it be a volatilization of a liquid, maybe a mist that's entrained as a result of the production of gases within an open process tank, right? And that mist then gets entrained into the exhaust system and can be blown out of the facility, or whether it be a solid material in somewhere, in a pneumatic conveyance somewhere. But again, those engineering controls, bag houses, scrubbers, if those aren't functioning and those aren't being inspected to make sure that they're functioning properly, then you're going to have a problem, right? It changes your whole release scenario. So that's why when we go out to the facilities, we want to make sure that all that equipment is in place. Again, it's being inspected, it's being maintained, and they should have inspection and maintenance specifications for each piece of control equipment that they're utilizing. And they should have records that they are being properly maintained. And that they should have backup equipment in place in the event that that system fails. Okay? How do they shut down a system if a scrubber fails? Do they continue to operate and you see a cloud of NOx going into the air, right? What do they do? What alarms are in place when those engineering controls fail? Because all those will drive how these materials get emitted into the atmosphere and how they're controlled or not controlled. Again, when it comes to training, same types of things apply for routine use. Okay? Again, the goal here is to develop that culture within the workplace for the employees. If the employers aren't doing their training, you're going to see it. But I encourage you guys, when you do your inspections and you're checking for the implementation of the RMP that says that they're doing training, interview employees. Ask them questions. Get a sense of their understanding. All right? That's going to be indicative of how well that program is being implemented at that facility. And ultimately how you're protecting the surrounding community from the potential hazards from that operation. And again, in short, it's very simple. By understanding the physical and chemical characteristics and hazards of the materials and processes involved, we can help industry take steps to minimize the potential for releases, allowing them to minimize the potential for negative impacts to human health and the environment. But it's understanding those very basic concepts, just like putting our shoes on in the morning, how simple it is, but we take it for granted, that we will better understand how those things are emitted into the atmosphere and what we can do to prevent that from occurring. Okay. I know it was quick, but again, I thank you guys for being here. Any specific questions?